We're covering three-dimensional space. So the Cartesian plane is useful to represent points in two-dimensional space. Okay, remember the Cartesian plane? We have an x and a y axis, and it's 2D space because we literally draw it on a 2D surface. It has one dimension, so the first dimension is x, and the second dimension is y. Okay, so that's why it's called two-dimensional space. So we now require a kind of new, and I use the word new in inverted commas because you'll see how the three-dimensional system is related to the Cartesian plane, the two-dimensional system. So we require a kind of new coordinate system to represent a point in three-dimensional space. So the Cartesian plane is a two-dimensional coordinate system, and it can only represent a point in two-dimensional space. It only has x and y. So x would represent a horizontal distance and y would represent a vertical distance. So to solve this problem, we add a z-axis to the Cartesian plane. And the z-axis can be thought of as the height above or below the Cartesian plane. And it's best explained in a picture. So what I want you to do is take a look at this. This is the three-dimensional coordinate system. Now your original Cartesian plane, it looked like, let's draw it down here, x and y. So here's the x and y Cartesian plane, and here's the y-axis and the x-axis. So the way it's drawn is a bit different. Here is quadrant 1 in the Cartesian plane, there's quadrant 1 in the Cartesian plane. So you're basically standing here, right? There you are, and you are viewing the three-dimensional coordinate system from this position. There's the positive x-axis, there's the positive y-axis, here is the positive x-axis, and here's the positive y-axis. Okay, so this would be quadrant 1 in the Cartesian plane. Quadrant 2, where y is positive, x is negative, that would be quadrant 3, and this would be quadrant 4. So just get the orientation right. Take a minute and look at the orientation. So that was the two-dimensional system, and you can see it's highlighted in this blue figure here. Now what we're doing, all we're doing is we're now taking a z-axis, and this is going to represent the height above or below the Cartesian plane. So this would be z is equal to 1, that's 1 unit above the Cartesian plane. Z is equal to 2 units above the Cartesian plane. Z is equal to 3, and so on. And then you have z is equal to -1, -2, and that's 1 unit below the Cartesian plane, 2 units below the Cartesian plane, and so on. So the z-axis is basically adding another dimension, hence three-dimensional coordinate system. And you can think of the z-axis again as height above or below the Cartesian plane. So just something that's important to note for terminology purposes in case you see this in a textbook. The two-dimensional Cartesian plane is called R2. Okay, it's called R2, and you say that as two space. Okay, because they are basically two coordinates that you have, an x and y coordinate, and it is in three dimensions. Sorry, not three dimensions, two dimensions. Then you have three-dimensional space, and that is called R3, which is known as three space. Why? Because you have three dimensions. You also have three coordinates now. So you're going to have an x, a y, and a z coordinate. So R2, two space, that was two-dimensional space, the Cartesian plane, that has two numbers for its coordinate system. Then you have R3, that's three space, three-dimensional space, and that has three numbers for its coordinate system, an x, a y, and a z. Now, before we work with 3D coordinates, we first need to understand 3D space a bit better. So when we visualize the coordinate system, the x and y axis are typically horizontal or flat. So when I mean visualize, I mean when you look at it, think about it, or even when you draw it. So the x and y axis you would have seen in this diagram here. We typically, by convention, we typically draw them flat or horizontal. So the x axis and the y axis, they look like that. So there's x, there's y, and then the z, we envision or we view it as the height above and below. Now, the direction of the portion of the z-axis is very important, and the direction is determined by the right-hand rule. So what I want you to do is I want you to go through the right-hand rule with me. So obviously by the name, take your right hand, and I want you to make this image with your right hand. So you're going to stick your thumb out, okay, you stick your thumb up, and then your pointer finger, you're going to point that forward. So basically you're making like the gun sign with your hand right now, and then bring your middle finger toward you. Okay, so all three fingers, and then leave your ring finger and your pinky finger attached or pointing to your palm. Those you don't have to point out. So basically your thumb, your pointer finger, and your middle finger are going to be at 90 degrees to each other. So it should be making this shape here. And this is how the right hand rule works. The y-axis is represented by your middle finger. The x-axis is represented by your pointer finger, and the z-axis is represented by your thumb. Now these are going to be in the positive direction of each axis. So the middle finger is in the positive, denotes the positive y-axis. The pointer finger denotes the positive x-axis, and then your thumb is going to denote the direction of the positive z-axis. So that's how the right-hand rule works. It just indicates if you have the x positive axis here, so that would be the x positive axis, and then the y positive axis here, does the z positive axis move downward like that? Does it go 1, 2, 3, 4? Or does the z positive axis move upward when you're drawing it and 1, 2, 3, 4? And in this case, this bottom here would be like -1, -2, -3. So the right-hand rule states that this is how you would draw the 3D coordinate system. Here's positive x, here's positive y, then your thumb is going to denote the direction of the z positive axis. So that's how the right-hand rule works. Also, another thing that I did not mention, I said when we visualize the coordinate system, the x and y axis are typically horizontal or flat. The key word there is typically. It is not a hard and fast rule. Sometimes, and you're going to see this, when we draw surfaces, it may be better to visualize that surface if you have to draw, let's say, the x and y axis like so, and then the z axis coming out. So the x and y axis would be kind of vertical, and then the z axis would move out toward you. So typically, when you do this, you draw the coordinate system like this. So there's x, there's y, and there's z. That's by convention, but it's not a hard and fast rule. Sometimes it's maybe better to draw the 3D coordinate system like this. And because we have different ways of drawing the 3D coordinate system, that's where the right-hand rule comes into play. So because we have that differences in drawing, let's say this was this portion here, that was positive x, and this is positive y. So what you're going to do is you're going to use the right-hand rule, and I want you to tell me, is this positive x, or sorry, positive z, or is that axis in the back positive z? So you use the right hand rule. Your pointer finger should be angling downward. Your middle finger should be angling here. And let's do it. Your thumb would be pointing in that direction there. So this would be the positive z axis. That's why we have the right hand rule. Because when we draw the 3D coordinate system a bit different, we know where the positive z axis is if we know where positive x and positive y axis, where they are. Now, additionally, just as the Cartesian plane is divided into 4 quadrants, so you had quadrant 1, quadrant 2, quadrant 3, and quadrant 4, 3D space is divided into 8 octants. Quad means 4, oct is for 8, so 8 octants. We can't really say 8 quadrants, it wouldn't make sense. So here's the 3D coordinate system. I found a cool image. So here's the positive x-axis, the positive y-axis, and the positive z-axis. Don't worry too much about what those are. I'll explain them now. Let's go for the octants first. And you can see in each of these diagrams, there's your positive x, positive y, positive z. So this first cube facing that is closest to you, that is octant 1. Then we go to the back, where x is negative, y is positive, and z is positive, that's octant 2. Then we go for negative y, negative x, and positive z, that's quadrant 3. Then we come to positive x, negative y, and positive z, that is octant 4. Then we have positive x, positive y, and negative z, that's octant 5. Next, we have negative x, positive y, and negative z, that's octant 6. Then we have negative x, negative y, and negative z, that's octant 7. And here we have positive x, negative y, and negative z, that is octant 8. So those are your octants. And let's look at what we have here. The xz plane, the yz plane, and the xy plane, those are what we call coordinate planes, and we'll learn about them later when we're sketching these surfaces. But basically, if you had to look at the 3D surface from different sides, so here's x, y, and z. If we have to, let's say, stand from the top and look down at the 3D surface, we won't see the z-axis, we'll see the xy plane, basically the xy coordinate system. Then, if we now stand from, let's say, here, so we are here, let's draw a person, and we have to look directly at the 3D coordinate system, we won't see the y-axis where we are standing on, we will just see the xz plane. Similarly, if we are standing, let's say here, and we are looking directly at the 3D coordinate system, we won't see the x-axis, we will just see the yz plane. So that's what these are. Those are coordinate planes. Now, if you ever forget the octants, or you forget how to draw them, or where octant 1 starts, you can use the below table. So how does this table work? Octant 1 is where the x is positive, the y values are positive, and the z values are positive. Octant, let's say octant 4. Octant 4 is where x is positive, y is negative, and z is positive. Okay, it also works like this. Let's say I give you a coordinate where we have a positive x, a negative value for y, and a negative value for z. That is going to be in octant 8. All right, and how do you remember this? So you can kind of see the pattern here. The first 4 of z are positive, and then the last 4 are negative. In each of these, in each x, y, and z, you're always going to have 4 positives, 4 negatives, and that's going to give you 8 values in total. Let's go for y. So it becomes positive, 2 positives, 2 negatives, 2 positives, 2 negatives. I think the hardest pattern to see is for x. That would be positive, 2 negatives, 2 positives, 2 negatives, and then a positive. So if you can remember this table, you're welcome to use it whenever you are supposed to plot it out. Otherwise, if you don't need the table, then you can use these drawings. You can use these drawings. However, I personally prefer the table. All right, let's do exercise 1. So plot the point P, and that has the coordinates 3, 4, and 10. And then I want you to identify what octant this point occupies. All right, let's do this example. So let's plot it first. So here's your x-axis. Here is your y-axis. And remember I said typically we draw them, the x and y-axis horizontally. And together the x and y, they make the xy plane. And in fact, this is a bit crooked. So let's just rotate it. There we go. Okay, and then we have the z-axis here. So this is positive x, positive y, positive z. So the point 3, 4, and 10. So we'll come 3 units out for x. Or in fact, let's draw 3 units out there. So we are going to go 3 units out. Then y is 4. So we will come 4 units out for y. And then 10 units up for z. So we will go 10 units up for z. That would be somewhere here. So the point 3, 4, and 10 would lie here. Again, I find it helpful to draw these red lines because it's difficult to kind of envision 3D properly on a 2D surface. which is this screen or the page wherever you're drawing it. So that's why I find it helpful to draw these lines. It tells us, okay, it's coming 3 units out for X, 4 units out for Y, and then 10 units up for Z. So it doesn't look like it's just sitting on the ZY plane. It actually gives it some depth. And what you can do is you can make little sketches if you want to, just to give it depth. So here is the point P, 3, 4, and 10. And now that you can see the depth of this point, okay, let's give it some more depth. Okay, so it's got depth away from the ZY surface. Okay, now that it has some depth and you can see it, you can see that this lies in octant 1 just from the diagram. So this lies in octant 1. Okay, and if you were using the table, you would just see that, okay, we have positive, positive, and positive. That's clearly octant 1. So you can use the table, but also it's important to be able to visualize this. So that's how you plot the point 3, 4, and 10.